And remember, any component present between input and output, you give the name for that component as it is a feedback element. This Z is a feedback element. Feedback means it can take some portion of output and give it back to input. So this Z is going to act like a feedback element, and this Z is going to make things difficult for me. So I cannot apply directly KVL or KCL if there is a component between input and output, or deriving an expression to relate V1 in terms of V2 is going to be difficult if there is Z present between V1 and V2. So if I decompose this Z into two separate components, I will have two loops, one in the input side, one in the output side. My computation becomes very, very simple. So that is what is Miller's theorem saying. Miller's theorem is more of splitting a component across two portions of a circuit. So I'm going to split the component, one at the input side and one at the output side. Okay, and if I split at the input side, I write it as Z suffix I. If I split at the output side, I write it as Z suffix O, Z naught. Zi is the value of Z at the input side. Z naught is the value of Z at the output side. And the values are given by Zi equal to Z by 1 minus A, Z naught equal to Za by A minus 1. So Z, it is in the, from the network I can find Z. What is A? A is going to be the gain of the amplifier. Gain means I am going to consider it is going to be an voltage amplifier. So I am going to consider the voltage gain. So A is going to be the voltage gain of the amplifier. So I can split a feedback component Z, which is present across input and output, into a separate component at the input side and a separate component at the output side using Miller's theorem. And I can even find what is the value of Zi and Z naught if I know A. A is going to be the voltage gain of the amplifier. And if you know what happens in resistance in parallel, so if you use the parallel formula and find the equivalent resistance, you will find you will get back Z. You will get back Z. Okay, so everything mathematically, concept wise, formula wise, everything has to be correct. Only then you can go for this theorem. So any doubt in the basic concept of Miller's theorem? So Miller's theorem is applicable wherever you see a component between input and output. For example, if I say in a common emitter transistor, base is the input, collector is the output. So if I have a resistor between base and collector, then I can apply Miller's theorem there because the resistance is between input and output. So if there is a resistance between base and emitter, I don't care because base is input, emitter is grounded, I don't care. If there is a resistance between collector and emitter, I don't care because collector is output, emitter is the grounded, so I don't care. But if there is a resistance between input and output, base and collector, that resistance can be simplified using Miller's theorem into one resistance completely at the base side, one resistance completely at the collector side. Okay, I hope the explanation for Miller's theorem is